Okay, friends, let's take a look at the probability distribution of taking a single fair six-sided die and rolling it one time. So I started it here. Generally speaking, there's a bunch of different ways you can display probability distributions. We'll look at one very simple way today, and then we'll look at other ways tomorrow. But the simplest way is just to create a t-table. So what I've done here in this column is I've put the result of the roll, and I've called that x. It seems that the letter X, we've talked about this before, is often used to denote data in statistics. So I'm just going to keep with that convention. And I'm going to say X is the result of rolling that single die one time. So you either get a 1, a 2, a 3, a 4, or a 5, or a 6. And then what you do next to that is you can put in the probabilities. So one way you can say this is say probability of that result. And that's totally fine. We're going to see a shorthand for that in a second. And then what is the probability? Well, I started with a die because we actually know what the results probabilities are. If you roll a fair six-sided die, there's a 1 in 6 chance, or about a 17% chance, that you're going to get a 1. And that's the same all the way down if you want to see it as a percentage right there. And if you want to increase in decimals, that's okay too, whatever you feel like. So that right there, my friends, that is a probability distribution of rolling a fair six-sided die one time. That's it. It's the outcome paired with its probability. Those are the 6 outcomes that can happen, and those are the 6 probabilities that go with it. Now, I mentioned that this is a little bit fictitious, which it is, because most of the time in your lives, you don't actually know the probabilities of the results. Okay, and I want to chat about that a little bit right now. I've set up in the back pages, I guess, of these spreadsheets. I've set up a die roller. So it effectively does the exact same thing that a real die would do. I can just keep rolling this six-sided die, and you can see it up here in the corner. I'm re-randomizing as we go. I'm going to hold it down and let it kind of do its thing. And as up here in the corner, this thing is re-randomizing over and over and over again. Down here in this next column, now please note, this is a frequency distribution over here. Not a probability distribution anymore. It's a frequency distribution. In other words, it's keeping track of how many total times each of these outcomes have happened. If I click over to this is keeping track of it exactly the same way. But what you're seeing now is you're seeing the theoretical chances that we wrote back in the first sheet over here. And these puppy dogs right here are what I like to call the empirical probabilities. Now, why empirical? I'm actually going to list that on here. I'm going to put empirical. And they're called empirical because they're the result of an experiment. And let's get fancy. I'm going to shrink the font down just because I'm that guy. So empirical just means it's the result of experiments. So if I keep rolling the die, you're seeing that those probabilities are changing. They are. They're definitely changing. I just realized something as I was watching this video and editing it. Those empirical probabilities that I've got in that spreadsheet, in case you're wondering where they came from, I probably should have explained this while I was recording it. I refer back to the previous sheet where I'm keeping track of how many times each of the numbers shows up, and then just dividing each of those numbers by the total number of trials. So the reason these percentages keep changing is, number one, the total number of trials keeps changing with each additional die roll. And number two, depending on what the outcome is, the number in that particular row goes up by 1 if we roll that number. So if the 1 gets rolled, then it pops up by 1. If the 2 gets rolled, it pops up by 1. But since the denominator is also changing the number of trials, you're basically just keeping a running total. Sorry about that. I should have made that clearer. Now, one thing is not changing, and hopefully you're going to understand this. If you add up all of these probabilities, it's going to sum to 100%, which hopefully that shouldn't surprise anybody. We don't think we need that many decimals. That shouldn't surprise anyone, right? Because 1/6 6 times is 100%. But here's what also shouldn't surprise you. These probabilities over here also need to sum to 100%. And the reason is quite simple. even though the empirical ones are not exactly the same like the theoretical ones are, they still represent the results of the experiment of rolling a die a number of times. Now, how many times have we rolled this die? I don't know, a few hundred by now, right? Let's take a look. Over 1,500 times now. You can see that is a fun little Excel cheat. If you select all the cells and then go down here, it'll tell you what they add up to, which is kind of fun. So 1,500 times. And what we've got here is just, now we're holding it down more, so it's rolling more than that. But 100% of the time, you have to get between a 1 and a 6. That doesn't change. So the reason I bring up this is called a Monte Carlo probability distribution, this one right here. This one back here is a theoretical probability distribution. And they're great right up until they're not. Because the only thing, honest to God, the only types of events that you can model theoretically that I can think of are dice, coins, and cards. That's it. Everything else that you observe in your careers has to be done empirically, which means you have to actually watch something happening over and over again until you see the results. But my dear friends, take a look really closely at these empirical versus theoretical probabilities. And what I'm going to do right now is I'm going to hold this puppy dog down and let them play out. We're going to increase the speed here so that things do speed up. And I wanted to get a whole lot of good data. So I let this thing run for, I think, 2.5 hours maybe. I actually went to Total Fit with my buddy Jenny Cruikshank and did some push-ups, did some jump rope, did some tuck jumps, and then I came back. And when I came back, this is what I saw. Now, you might notice that still the empirical probabilities are not exactly equal to the theoretical ones, but they're one heck of a lot closer to the theoretical ones and each other than they were when I started the replications. And just to say it one more time, in your careers, in your lives, empirical probabilities are more useful than theoretical ones. I'm starting with theoretical ones just to get the idea of probability distributions understood, because we're used to dice, we're used to coins. But most of the time in the world, we're going to have to observe repeated trials or something before being able to establish probabilities. But that being said, let's look at a probability distribution or two or three with coins.